Hello, Core 1 students. I can't quite remember the last time that I made a video. Oh, it was the quadratic regression delta math. But anyways, it's been a minute since you guys have heard from me verbally speaking. And I wanted to go through the first two note sheets because what you guys have been doing is some delta to kind of ease into quadratics, but you've also done the website exploration where you began some preliminary investigative work on the quadratic function and its graph, which we often call the parabola. And then we're going from there to part two to kind of figure out the nitty gritty, right? We've got these variables, the variable x, which is being squared in a quadratic, but then there's also just a single x. So there's the ax squared, kind of if we look at the quadratic right here, right? There's the ax squared, there's the bx term, and there's a c term. And what happens when we change those letters? In other words, we call those the coefficients. A and B are the coefficients, and C is the constant. So let me run down and just give you a verbal explanation to these two keys. If you haven't corrected your first key yet, this would be a great time to pull that out and do that. And then we'll go to the second key in a minute as well. Excuse me. I'm filming this at 9:35 p.m. on March 23, so Monday night. So here we go. The first one. So standard form for a quadratic equation. Just to give you an idea or a connection, standard form for a linear function is y equals mx plus b, right? That's the general form that we put it in, and you kind of put your variable x first, and whatever coefficient m that goes with it, which we also commonly know as the slope. In this case, a quadratic standard form is ax squared plus bx plus c. And a is not the slope, b is not the slope, c is not the slope. These letters are no longer determining the slope of your quadratic. Your quadratic is different than a line. It gives you a parabola graph rather than a line. So just try to get that out of your system, that a is not the slope and b is not the slope. I know that they're being multiplied by our variable x, but it is not the same thing as an equation y equals mx plus b, where m is our slope or our rate of change. So you got to kind of keep that separate. But anyways, let's go back in reverse. The name quadratic, where does that come from? Well, the word quad, oftentimes you think of four, right? A quad motor vehicle or toy that's got four wheels. When I was in college, there was a dorm room on every single floor of the dormitory building that was called the quad, because instead of two people living in the room, it was a bigger room so four people could live in it. But it also means to square, right? A square has four sides. And so squaring something, in this case, is the type of application we're using the word quad for. And then since it has the two, we also call it an equation of degree 2. This is language that, right, the word degree, that is something that we won't cover until Core 3. So this is a really cool tidbit, but if you don't remember that, you're totally fine. All right, so standard form y equals ax squared plus bx plus c. Note, if you continue to do work in a Google Doc, you can write exponents by doing insert equation. So that would be up here. So insert equation. If you were doing it in Microsoft Word, you would want to go up to the top toolbar, not in Microsoft Word, but the very, very top toolbar, and you can insert an equation that way in a similar way as well. Okay, letter C. A coefficient of a function is a number in front of a variable. So for example, my variable is x, and x that means that a and b are going to be my coefficients because those are numbers in front of the variable x. Now, x squared is a variable. It's just two x's being multiplied by each other. So a and b. So the most common variable is x, like we said. So for standard form of a quadratic, right here, this is our standard form, the coefficients are a and b. Now you might say, what about c, right? Why isn't c get to be called that as well? Well, we'll get to that. But basically, in short, c is not multiplied by a variable. It's just by itself. So it is not a coefficient. So now the coefficient a can never be 0. Because if you think about it, if I made a equal to 0, that just gives me a horizontal line, not a quadratic equation, right? A can't be 0. And if I change my b, it's pretty much like I've got a linear function now, where it's y equals x plus 3, because my a, if you multiply anything times 0, and this is a times x squared, if I make a 0, well, 0 times x squared will always be 0. There's that 0 product property, and we can't avoid that. So we always want a to be either to be non-zero, so either a positive number or a negative number, but never 0. Letter D, a constant is a term in an algebraic function in which a variable does not appear. So like what we have with c. So for the standard form of a quadratic, the letter that represents the constant term is c. C does not have a variable following it. We're not multiplying c by a variable. So c is a constant, and luckily enough, the letter c is the first letter of the word constant. So it works out quite nice. Now, let's practice identifying what these letters should be, a, b, and c, depending on what these equations are that they give us. So the first one, 3x squared plus 6x plus 1. Well, the a always goes with my x squared, like what we have up above. So my a is going to be 3 because it's 3 times x squared. My b is going to be 6 because it's 6 times x. B always goes with the singular x variable. A goes with the x squared, b goes with the x. It's kind of like like you're going down. You go x squared, then x, and then nothing. And then with the ABC, we're going up in the alphabet. So there's patterns here that you want to recognize. For part 2, x squared plus 7, there are only 2 items in this equation, x squared and 7. Now, technically, see this little note here, there is an invisible 1 out front of the x squared. 1 times anything is itself. So 1 times x squared gives me x squared. So that means we've got a is 1. B is going to be 0. Because if I multiply 0 times x, it disappears. And right here, it disappeared. It's no longer there. And then last but not least, we have our constant number. And that is going to be c equals 7. Last but not least, 2x squared plus x. I've got my leading, right, my x squared, kind of the big grand item in my equation, x squared. Well, what goes with it? A, and in this case there's a 2, so that is a equals 2. My b, now similar to part 1, there's just a 1 in front of the x. Anytime you multiply 1 by something, it gives you x. It gives you itself. So 1 times x is just going to give me x. So b equals 1. And now there's no constant number, notice, at the end. So that means that the constant will just be 0. Because 2x squared plus x plus 0 is the same thing as 2x squared plus x. All right. Now, feel free to pause this page. I'll leave it here for a minute so you can see the whole thing. Feel free to pause this page to correct your first page of your notes. Hopefully you did this already, but if you got busy with other stuff and you need to do that now, please feel free. All right, last page of this is graphing basics. So click on the link and it takes us to here. And we should we should change A, B, and C and see what happens. So how could I make the mood? So now this is a parabola, so we essentially are making happy faces and sad faces. It's kind of our way to keep that straight. So if I want to make my quadratic happy, you should have noted that, well, if I change B, it doesn't really make it go happy or sad. If I change C, it doesn't really make it go happy or sad. It just raises it up or down. But if I change A, when A is negative, when A is a negative number, it's facing down, so it's a sad face. But when A is positive, it's a happy face, or I guess you could say a smile, an upward facing one. So the A value, when it's greater than 0, when it's positive, it's going to be happy, and when it is negative, so less than 0, it's going to be sad. No, A cannot be 0, because if A is 0, then we would have an equation that looks like y equals bx plus c, which is linear and not quadratic. Let me change that. Next, the width. So the width of a quadratic is either going to be narrow, normal, or wide. So if I were to make my A value greater than 1 or less than negative 1, so if I put it at 1, 1 is typically regarded as the standard, or the, I guess you could say the parent function. Where when A equals 1, that's kind of considered the norm, the normal quadratic. So, but if I make it anything greater than 1, it gets narrower and narrower. And if I make it anything less than, so we got negative 1 here, kind of the normal, the norm. If I go anything lower than negative 1, it's going to get skinnier and skinnier. So, when is it narrow? When A is greater than 1 and when it is less than negative 1. Again, what we said, the normal, right? It's when A equals 1 and when A equals negative 1. And then wide, as you might have a harder time seeing, but the wide is when, so if A is at negative 1, and that is the norm, if I can get it there, how do I need to change it? Do I need to move the slider down, or do I need to move the slider up to make it look wider? And how far up can I move it, or how far down can I move it until it stops or flips? So if, again, like I said, if I move it down, I'm making my A value more and more negative, so it's getting narrower. Let's make it into like a decimal. That's definitely making it wider as I get closer and closer to 0. But again, if I actually hit 0, it's a flat line. So basically, anywhere in between 0 and negative 1 will give me a wider quadratic in comparison to the normal, where A equals just negative 1. Let's do it with positive 1. So if A equals positive 1, then we are going to want to move the cursor down, so it's a decimal, a positive decimal, to make it wider. And so that's how we would represent it here with inequalities. A is going to be greater than 0, right? Not ever equal to it. Greater than 0, but less than 1, aka a decimal. Or A has got to be greater than negative 1 or less than 0. So basically, A is in between 0 and negative 1, and A is in between 0 and 1, aka positive and negative decimals. Now, the vertex of a quadratic is the maximum point or the minimum point of a quadratic function. So the vertex is a minimum point, which is an example right here, because this is one low point. Now, there's not a maximum point because this goes on forever and that goes on forever, but there is a point where I don't go any lower. That's my minimum point. Now, when is this the case? It's the case when A is positive, because if I were to flip it to a negative number, that's no longer the same scenario. So when A is positive, I have a minimum value, but when A is instantly negative, I switch. I now have a maximum value, a tippy top value of my parabola, where this goes on to a negative infinity, that goes on forever, right? So I have a maximum height of my parabola. And now finally, last but not least, the y-intercept. Which letter determines the y-intercept? I don't know if you noticed, but when I move this cursor for C, let's move it to 0. If I move it to 0, it should be crossing through the origin. Oh, it should be crossing through the origin. My y-intercept should be at 0, 0. It sure is. Now if I move it up to 4, my y-intercept should be 0, 4. 0, 4. There we go. So the letter C is what determines my y-intercept. It's super nice. Just like when the equation y equals mx plus b, 0, b is always your y-intercept. Similar idea with a quadratic. 0, c will always be my y-intercept. Now that's a perfect segue into the second part to my notes. Now this is all a review as to what we just did on the last note sheet. Now, one thing I want to mention to you guys, and this is something that we corrected, it showed up here when we talked about the width and these three pieces, but we forgot to mention the fact that we're going to have a positive a value and a negative a value, where we're having a happy parabola and a sad parabola. Where we've got three different scenarios for narrow, normal, and wide. Narrow, normal, wide for the width. So just if you want to change this on your own or whatever it is, or maybe you want to just print this key out and have this as a reference or just refer back to this as you go forward, that's great. But just take note, this part is different from your original one that we gave you guys. Now, this is all review, but we start here. Let's try one out. So let's give us the function. This is the parent function, y equals x squared. The parent function for a linear function would be y equals x. It's the most basic form of a quadratic or of any function that you would have. So the most basic form of an exponential function would be y equals 1 to the power of x. For a quadratic, it's y equals x squared. For a linear, it's y equals x. So in this case, what are my coefficients a and b, and what is my constant c? So a is going to be equal to 1, right? There's that invisible 1 out front of my x squared. 1 times x squared equals x squared. So my a is 1, but I don't have a b. I don't have an x or a constant number. There's nothing else. I only have x squared, so that means my b is 0 and my c is 0, because anything times 0 is nothing. Is this a happy or a sad parabola? This is happy, so it's opening up, which makes sense because a is positive. Now the width is normal. Key word here, normal, because a equals 1. You got to look at your notes. It's a normal when a equals 1. That's the width. Now the vertex is going to be a minimum point because a is positive, right? If we look at the vertex here, the vertex is going to be a minimum point when a is positive. So here we go. It's a minimum point. And then finally the y-intercept is going to be 0, 0, because it's always going to be determined by the c value. If my c value is 0, then my y-intercept will be 0, 0. Now, why do I know that the x value is always going to be 0 here? Well, a y-intercept always occurs when x is equal to 0. And then the y value that corresponds with it to make the coordinate just depends on where you cross the the y-axis. Now, parent function number 2, the downward-facing quadratic. Y equals negative x squared. So this is going to be very similar to the first, except for it's got a negative a value, and it's negative 1. Negative 1 times x squared gives you negative x squared. B is going to be 0, and c will also be 0 as well for the same reasons as I explained before. There's nothing else in my quadratic. There's no x term, there's no c term at all. It's just the x squared. So that means b must be 0 and c is 0. Now, the mood, it's sad. It's going down. The width, it's normal because a equals negative 1. Just like what we determined in our notes. When a equals negative 1, the width is normal. And then the vertex is going to be a maximum because it is a downward facing parabola, so we have a maximum most point. And then also 0, 0 is my y-intercept because that is the tippy top point in this case. All right, last page. We've got a couple of different types of functions that are in incomplete form. So we've got y equals ax squared plus c. So when I'm missing my middle bx term, or when I'm missing the bx, what or how does my information change? So let's say I make my bx equal to 0. Now, how do I determine if it's happy or sad? Well, happy and sad is still determined by when A is positive or when A is negative. It's negative, it's sad, positive, it's happy. So when A is greater than 0 and when A is less than 0. The width, same idea. When A is greater than 1 or when A is less than -1, we've got a narrow quadratic. When A equals 1 or -1, that is normal still. That has not changed. Now the same thing will be for when it's considered wide, when it's a negative decimal or when it's a positive decimal. Now the vertex, right? The maximum minimum point, how does that change? Well, it's determined by where your C value is. The vertex, your minimum point, is going to be the same thing as your y-intercept because this is perfectly symmetrical about the y-axis. You see that? It's perfectly split down the middle. So my minimum most point is going to be the same thing as my y-intercept here. So 0, c is the y-intercept, but also the vertex. In this case, the minimum point. Now, feel free to ask questions about this. But last but not least, what if I have an incomplete quadratic where I'm missing my constant? So let's say my constant is 0. How does that change my graph? Well, notice, let's make it at 1. Let's try to make it normal. Okay, so here, there's a couple of different things that we want to look for. First, the y-intercept. Where is the y-intercept going to occur? If I change A, does my y-intercept at all change? Where is it crossing my y-axis? Is it always at the same point? And when I change B, is it always at the same point? It looks like it is. That orange circle, right? Focus on this orange circle. That's the y-intercept. Does that change at all? It shouldn't. So 0, 0, that origin point will always be the y-intercept when you have a quadratic without a constant. Now the x-intercepts, when I cross the x-axis, those are going to be different. Let's make my a value be, let's make it 2. Actually, let's make it 1. Yeah, let's make it 2. Now, when I move b around, let's make b be 4. When b equals 4, my x-intercepts are at 0 and -2. How did I get from to -2? Well, if I put a to b at +1, if I can get it there. There we go. You'll see that the x-intercepts, where it crosses my x-axis, is at 0, x equals 0, and x equals -4. It's just the opposite of b. But once I change my a value up to 2, it switched. So really what I'm doing is 0, 0 and the opposite of b divided by a. Now, these two pieces, good to know, but if you don't remember them, that's okay. There's other ways for us to determine the x-intercepts without having to remember this rule. Same idea for the vertex. The vertex, the minimum or the maximum point. Notice here, it's going to be at -1, -2. Opposite of b divided by 2a. Opposite of b is 4 divided by 2 times a, which is 2, is going to be 4. -4 divided by 4 is -1. And that gives us our -1 x value. This piece right here, I want you to maybe try to see if you can make a connection, but we're going to dig deeper into that later on in Core 2. Now, last but not least, a cool result is when b is negative. When I make b negative, it shifts my quadratic to the right, right? I'm shifting to the right. But when I make it positive, I shift to the left. So I'm shifting to the right when b is negative, and I'm shifting to the left when b is positive. It's a flip-flop situation here. It's the opposite. So when b, the middle term, right, the b, when that moves in the positive direction, I'm going to go to the left and towards the negative. Kind of weird. But when I make it negative, I'm actually going to the right. I'm going in the positive direction. Also kind of strange. But also kind of will make sense eventually once we dig into the algebra behind all this. Now, this video got extremely long. It's about 25 minutes long. So feel free to skip around. If you already made it and this is all making sense, maybe part 1 was like perfect sense and you want to skip to here, well, you're at the video now, so you probably didn't have any idea to skip. But anyways, all good stuff. Now, what I want you guys to do is go to the Delta Math assignment and practice just working with a lot of these coefficients. I think you should go pretty quick and not take too long. So 25-minute video. Hopefully get done with Delta in 15 to 20 minutes. Let me know if you have questions on the Google Doc, and we'll go from there.